you're going to use it. What if it's a rectangle? Yeah, so the rectangle is what? 1.5 V over A. So that's a shear stress for a rectangle. And then there was one more. Circle. There was a shortcut for a circle. I will give you one of those. So if it was something other than that, you could look up a shortcut. If it was like a C shape or something, there might be a shortcut for that. I think there is actually. C shape would be, anyone? Yeah, it could be those, but they don't actually give you the shortcut for this. But what's the shortcut for this one? It is the rectangular section of the W shape. So the shortcut for this one is the same thing. It's the rectangular section of a C shape. Yeah, this is a C shape. L shape would be the same thing. So this again would be that. And then an L shape is again that big rectangular piece. So anything that's kind of tall and has flanges sticking out, the shortcut is just the vertical mass for the area.
That's all labeled in the tables the same way as G and 2W.
Yep, I believe it is. Yep. You might, I mean, it could be. We can look real quick. If it's not, you just can determine it, right? But I think they do call, I don't know if they call it the web on a C shape. I think there is L shapes. So the L shapes they call, I don't give it to you. Yeah, I don't give it to you. On the L shapes. Oh yeah, they give it to you in the designation. But they don't call it TW. They just say it's a L 6 by 6 by 1. That would be 1 thick for the L shape. So you'd have to go 6 times 1 to get the vertical web. The C shape, they do call it TW, thickness of the web. So they do call it TW here in the C shape. So yeah. No VQ over IV, no, because we don't have time to decipher the Q part. These three things you can figure out because we've done inertia and we've done shear force, but Q takes a little more time. I mean, it's not super difficult concept, but it takes a long time to do it if you have a complicated shape. It's called the statical moment, Q is. So if it was a 2 by 6, just a rectangle, where the neutral axis is here, the statical moment is the area above and its centroid multiplied by the lever arm. So it's a moment, it's an area moment. It's very odd. But you find this area, you have to know where this is, which is pretty easy to do because it's a rectangle. And then you multiply it by this to get Q. So they call this typically Y, and they call this typically A. So Q equals Y times A. It's a moment, but it's an area moment. It's like really odd. But, you know, simple rectangle, piece of cake. But man, if you start looking at a complicated shape above the neutral axis, you have to break it into small pieces to each area moment. It's like it's really complicated. So not necessary. You shouldn't be doing it out there either. So if somebody says, hey, go do this for you, it's like, with a 2-year degree? No, that's not my job. That's somebody else's job. All right. Help, Nick? Does that help? Yeah. Yeah. So I'm thinking you will have to do a shear stress on the final. So you will have to use one of those. The final is going to be one problem worked from the beginning, similar to what I'm going to do right now. It will require you to remember how to find the neutral axis. So I want to go through that. There's a chapter on it. You can look at the formulas. It'll come back to you, I think. And it'll be a simple one like this, rectangles type of thing. Okay. But it'll go from the very beginning statics through finding where the neutral axis is of the shape, and then finding the inertia of this shape. So we'll have to review that. And then doing the statics, and then doing the shearing moment diagram, and then calculating a bending stress and a shear stress. So a lot of parts and pieces, but kind of one problem all the way through. Like Max asked earlier, if you screw a part of it up and then keep working, I'm just going to look at what you did. I'm not going to look at your numbers, but you took the bad number down and you did this with it. That's correct. So no point lost there. Okay. So it won't be like, oh, you screwed the first part up and then you screwed the next 9 up because you used a bad number. That's not cool. I'm not doing that. So you just want to focus on doing each step correctly going through. Try not to make a mistake, but if you do, that'll just be that one mistake. All right. Okay, so this problem is, what number is it? Number 5? 14.5? Yeah. Yeah, I'm recording it, and we did it like as a homework problem, but not everybody did it, I don't think, because it is from the get-go. Like, and it's kind of worded weird, and it even looks weird, so. I'm gonna show you it. Yeah, for some reason I can't find it. Oh, it's in the wrong chapter. 328. So the problem is number 5 down here, but it refers to this diagram 14.2. Well, this diagram 14.2 is a cross section. It's the slice of the beam. So that's what you had to figure out. And then they said, oh, assume this timber member, this thing up here, is used to simply supported, which means it has supports at the end, simply supported. 12-foot span, carrying this uniform load, 500 pounds per foot, given the load. The given load includes the weight of the beam, so we don't have to do any of that. Calculate the maximum induced bending stress. Okay. So it gives you a cross section that's not defined as far as where the neutral axis is, and it gives you the cross section that's not defined as far as inertia goes. So those two things got to be done. I would do them first before I started into it, but you could do the statics first and then do the inertia part. Doesn't really matter. So that's the one we're going to grind through. And since Ruth just came in, it'll be just like the final, Ruth. So this is going to be essentially, the final is going to be one problem where you work all the way through it from the beginning, but you'll get points as you go through the problem. And I might even break it up into like number 1, you know, find the inertia, or number 1, find the centroid, number 2, do the statics, number 3, you know, that kind of thing. So you'll break it down. It's your choice, and I'm going to send a little email survey out because some can't come next. So sounds like it's feeling like it's going to be online next week. So if we do that, I could give you a practice final Thursday. So that might be fun too. Good way to go. So, and again, Thursday can be, since that was when I wanted the final, that can be online or in person. I'll let you tell me as far as the group goes. Okay. I'll send an email out on that. All right, so let's do the why. The first thing you'd want to do is neutral axis. You want to find out where this thing is. They drew it in, you know, in the problem, knowing that, hey, you got to find that. That's part of the first part of the problem. It is part of this term and this, you know, in this book. So it's good for us to refresh that, because you do have to do this fairly often. Somebody will take a W shape or a C shape and then add something to it, and boom, you got to do this then. So I wrote the formula down just as a reminder. That's my summation. This is 14.5, 328. So it uses this cross section from 14.2, and then it puts a load on it in the words of 14.5. So this is the cross section, and the beam, they don't give you a drawing of it, but essentially the beam looks like this. It's just not 400, it's 500. So 12-foot span, 500 pounds per foot distribution, and that cross section right there. So before I go into the statics part, I would probably try to find Y bar, the location of the x-axis. So that's a good thing to remember. Y bar is the location of the x-axis, which is what we need. And then we'll need the inertia about that x-axis. So Y bar first, remember it's the summation of Y's times A's. And these are the individual Y distances and the individual areas. So we have two of them, there'll be two statements up here. If you had three, there would be three statements. If you had four, there'd be four statements, right? So I'll just kind of work slowly. You can work ahead of me. I think that's actually supposed to be switched. So areas times Y distances, you see I set my axis up here, so I know where I'm coming off of. The Y distance to that upper shape, 10 plus 1.5, 11.5. The Y distance to the lower shape is half of the 10. And then the area is 10.4. And then down below is just the total area, right? If you had a hole, what would you do with it? Yeah, subtract it from the area and subtract it from up above. So you treat it like a solid, but you just put a minus in front of it. If somebody borrowed. Yep. So that is the distance to the upper shape. So 10 to here and then half of the 3. Yep. Yep. Same way that I got this 5, right? Half of the 10, this lower shape. All right, so now we crunch it. $8.079. So then you kind of look at that and you just want to, say, hey, common sense says, yeah, that's kind of where it should be. It should be slid up because of the mass up above. So that's good. So now we need the inertia. So the way we did inertias was a similar process where we do the individual inertia of the individual shape, right? And then we move those to the neutral axis. We have to transfer it. And that was the transfer formula. So the inertia of this shape we called I sub O. It's like the original inertia or the inertia of that original shape on its own. So that's this one and then this one. And we just do that in position. So the inertia we're finding is the inertia about its own centroid. So this one, and I have it memorized, but it's in the book. It's base height cubed over 12. That's a rectangle. And you can use that same formula for any rectangle in any position, because what gets cubed is the height, right? Each time. So, but that gives us inertia here. To get it here, we have to transfer it. So the first step is just to find these original inertias about their own axis. So the base is 12, the height is 3, and that's cubed over 12. $27. Anybody else get that? Okay, good. And then we have to do the other one. So the other one is here. It's neutral axis of this 10 high by 4 shape is 5 units up, and it's right here. So now we need the I O of that shape. And if I numbered the shape, you know, you'd stick a number to it, but I'm kind of drawing arrows instead. Again, base 4, height 10, cubed over 12. So you use the same formula, it's just the base and the height switch. And it makes sense, this tall piece is going to be a higher inertia than a flat piece. So much bigger, 83.33. Oh, that sounds better. Wonder what I did wrong. I'm glad we're working as a team. Oh, 1,000, that's much different. 4,000 up above. Yeah, I lost a decimal place somewhere, didn't I? Brilliant using a pencil today. 333.3333 inches to the 4th. All right, so those are those individual inertias. So that's step one when you're trying to find a complex inertia. You got to find the individuals first. Then you got to transfer it. So the transfer formula was I sub O plus AD squared. That's how we get this inertia to here and this inertia to here. Once they're at the same location, we can add them together. That's the rule. We cannot add them together if they're not at that same, on that same axis. So that means that we need I sub O, which we just found for both of them. So we have that. We need area. That's pretty easy to get for both of them. But we need the transfer distance. That's D. So the transfer distance for this upper one is right here, D. And then the transfer for the lower one is right here, D. Right? Axis to axis. So however you want to get that, whatever works for you. For this upper one, I would say it's 10 plus 1.5 to get to it. And then if I subtract Y bar from it, I get D. Yeah. And then the same kind of process with this one. I know Y bar and I know this one's at 5. I subtract one from the other and we'll get that transfer distance also. And I'll just write them in position if I can write small enough. .421 here. And that's inches, transfer distance. And then this one is going to be the 8.079 minus 5, because that's 5 to its original position. 3.079. That's here. Even made a big drawing and it still gets small. Little d in here. So now I can start transferring these inertias. So I'll do the top one first. That was 27 for the inertia about its own axis. And its area was 36. And then its transfer distance up here is 3.421. And you cannot forget to square it. Super easy to forget to square it. $448.316. And then the second one. Once you get done with those two transfers, then both of these inertias are at the x-x axis. So sometimes I put this notation down, which just reminds me, hey, I've transferred it to this axis now, this x-x axis. That's where they're both at. I can add them together. 1160.856. So kind of review that process. When you're doing inertia, you find those individual inertias first, and then you have to transfer them to the neutral axis. If they're not already there, sometimes one will be there and you have to transfer the other, that kind of thing can happen. But in this case, we had to transfer both of them. Once they're there, then you can add them to get the combined inertia. All right. I wrote it up on this page, so we'll have it. This one's going away. Once you get those two things, you got Y bar, you've got the inertia. We could get the area of the whole thing easy enough. So you have everything you need to work your way towards MC over I. Right? That's bending stress. Or if we did shear stress on this one, it would be that crazy VQ over IB. So I wouldn't probably have you do that. That's why they didn't ask you to do shear stress on the problem. So we won't do shear stress, we'll just do bending stress. We can't do deflection either because it's not a beam out of the back of the book. Yeah, it is a beam out of the back of the book, so we can do deflection. All right, so let's now look at the statics part. So we kind of leave this behind for a second. It's all good work, but they say it's simply supported. So anytime they say simple support, that means it's just supported at the ends, right? And if there was a side load, one of them would be a pin to carry that side load. Couldn't have it on two rollers. It would just roll away. So they say it's 500 pounds per foot, 12 feet. So we can come up with the two reactions fairly easy. It is a beam that matches the back of the book. So I could use the back of the book. Just know that that's a distribution. If you want to use it, you can. I'm just going to draw them because the test will probably say draw a shear moment diagram. If it exactly matches the back of the book, then you could look at it to verify that your shear moment diagram works. So we have 12, 500 times, and then 2 divide 3,000. So then the diagram would be shear and moment. We know it just follows the forces, and the shear comes up to 3,000. Comes down at a consistent rate to the other 3,000, which then it goes up. Giving me a Vmax of 3,000. So then we know the moment starts with a lot of positive slope, gets down to very little positive slope, and then goes to 0 there, and then heads off to be negative and more negative and more negative. So it's going to start with positive slope, go to less positive, go to flat, go to a little bit of negative, and then more negative. So really read the pluses and minuses in the shear, and also where it crosses is a maximum or minimum in the moment. So that means M max. I can get that from the shear diagram, the area of the shear. I'll just do that. It's 1/2. The base is 6 feet. And times the height is 3,000. That's going to give it to us in foot-pounds. Should be 9,000. Okay, that's good. It's positive. That's just because that deflection curve kind of is concave. Smiley face in the deflection curve means it's positive. This also means it's positive because it headed up. So then we would work our way towards bending stress, which is MC over I. Yeah, go ahead. Yeah, so C is going to be from the neutral axis to the outermost fiber. the biggest one? Because often there's two. And we have two, because our neutral axis is here, right? And so this bottom section, it's 8.079 is one C distance, and then the other C distance is up here. So you got to figure out what that one is to see which one's the biggest. So the way I do that is I know the overall height is 13. Yeah, so then I take that away from it to see what that upper one is. Yeah, so it's much smaller than the 8.079. That's right. You want to use the greatest C value. 8.079. So, and I just wrote this other version of the equation because if this was a common shape, you can just look up SX and use it. This is not a common shape, so we have to use C and I, which we already calculated, so we're good with that. So our moment is 9,000 foot-pounds. Our C value we determined was 8.079 inches. And that was from this Y bar, the bigger distance. And then I, which we got at 1160.856 inches to the fourth. That's this guy. So this all should boil down to PSI, pounds per square inch. So we have a foot problem here. That just doesn't work with these inches. So we need to get it to inches. We have 12 inches per foot multiplier, and then those cross. And now we're going to have inches squared above, inches to the fourth below. So we're going to be left with pounds per inch squared. That's what we want. Anybody got a number? Yep. I'm just going to say 6.3 PSI. Yep. And if I said it was Doug Fir, then we would do what? Yeah, we would check it. That's why we're doing it. Is we want to check it compared to the tables. Bending stress for Doug Fir, I think that was 900. Yeah. So we're good. £500 per foot. That's a lot. It's a lot of load. This is a 10-inch by 4-inch. It's a lot of lumber, like in that cross section. So deflection would be the other piece. So we're doing deflection by the formula method, which means I got to find a beam that has a uniform distribution throughout, simply supported, that matches, the same loading condition. There should be one back there. Yep, simple beam number 1. That is 503. 503, simple beam number 1. Let's just go through the options here, because there's more things than you're going to use, but you could verify R and V. I mean, we came up with a maximum shear of 3,000, but it's saying that the shear and the reactions are the same. These are the reactions out here, and that's true. We got 3,000 for the reactions, and we got 3,000 for the shear. So that's what this first thing's telling us. The second one, V sub X, is the shear at any X location. Well, we don't need that. We just need the maximum. And that's what the first one was. So there's some things in here you won't use, right? On problems like that one. If you did want to know, hey, what's the shear at 3 feet? Well, you could get it with this equation here. Then it's moment max. It's saying it's at the center, and it's WL squared over 8. W is the load condition. That's a distribution. They use W for that. L is the length of the thing. That'd be 12 feet. And you're going to square it and then divide by 8. And you should come up with what we got out of our moment. Our moment was what, 9,000? Yeah. So you could test it by running this equation. It'd be 500 times 12 squared over 8, and that would be foot-pounds. W is the distribution because they call this WL. Yeah. So I don't really like that they put the W and the L right here in the little diagram because W is the distribution, right? To get the load, you go W times L. So W is the 500, L is the 12 feet. Yeah, so. Yep. I see squared, WL squared. Oh no, I'm doing M max still, sorry. I'm not down there yet. Yeah, that's to the 4th. Just the L, yep. I don't see to the 4. Oh, delta max at the center. Yep, right there. Absolutely. Yep. Absolutely. Yes, 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 yes. Yep. So I'm going to check their moment, make sure that works.
We would want all the lengths, right?
9,000. For the moment, you can leave it in feet or inches. It's up to you. At some point, it's got to get to inches. So, because E is going to come to you in inches squared. So I just worked through this one, the max moment, and checked it with our max moment. And it was 9,000. It worked out. They're jumping to deflection because they know that's where we're headed. But I'm going to go through each one just so you understand what the heck these things are. So they give you M max, right? That's going to be your maximum moment right here. But then they give you an MX, and that's at any X location. So if somebody said, hey, what's the moment at 4 feet? You would use this equation. So again, we're not going to use it because we just want the max. But that option is there on all of the beams to get information about anywhere on the beam. Okay. Then delta max, that's what we would want for the deflection. 5 WL to the 4th, 384 EI. So I'm going to write that one down. Delta max, 5 WL to the 4th, 5 WL to the 4th. Try to make them a little cursive. 384 EI. So that's the deflection of this beam. And it's based on the load, that's this W part, and the information about the cross section, which is I. So that's how that area information comes in, is in the I inertia category. And then E would be modulus elasticity. It's what the material is. So that's Doug fir, because we called it Doug fir. So then I'm going to write it out and try and get the units all correct. 5 W was 500 pounds per foot. L is 12 feet. And that's to the 4th over 384 E. Doug fir. Yep, 1700 KSI or 17. Yeah, 17 to the 5th PSI, right? Yeah. So I'm going to write it 17. I'll put brackets around that. 17 E to the 5. So that E is exponential, not modulus elasticity. Pounds per inch squared, because I know I'm going to need it in inches squared and pounds at some point to get these units to cross. So I took their 1700 and just made it 17 to the 5th. Because it adds 3 zeros to the 1700. And then I was so long ago, what was it? 1160? 0.85 inches to the 4th. And we got the I from up above where we calculated it. So lots of stuff going on here. Lots of moving parts. We know in the end, we're going to want inches of deflection. That's good. That's what we want this in. So that means the feet got to go away. And there's a bunch of feet here, right? Feet to the 4th, feet down below. So really there's feet to the 3rd. So I need a 12 to the 3rd inches per foot. For the conversion to get these feet to inches. Now all of those feet go away. And all the units work out then. Pounds go away, inches squared flip up, combine with these inches to the 4th down below. So yeah, it's a bit of a unit nightmare, but if you get it all to inches, it will work out. Now I got to calculate it though.
How do you do scientific notation on theory?
That's a great
I've
question.
always just done 10 minutes.
That's the way I do it. Yeah, I think that's fine.
It has the E button, 4 different E buttons.
Yeah, I don't really know. I'm an HP guy, so
Is there an E?
yeah, is there an
There's
E?
an E, try that one, it's still giving me that. What about the lowercase? I think that's its own number. Yeah, that's.
Yeah, that's the log thing. Yeah. Yeah. I get 0.1, I'm gonna say 0.12 inches. So there's no way to compare that to anything unless it's given in the problem, right? There's no deflection limit given in this problem. But we can use the 1 to 300 just to kind of compare it. So a typical deflection allowable, especially with the wood industry, is 1/300th of the span. So we have what, 144 inches, 12 times 12, right? And then 300 divide. It looks like a limit might be 0.48. On the problem I give you in the final, it'll probably say a limit. I'll just give you a limit, like builder, structural engineer, holds all deflection limits at 0.25, quarter inch or something. Yeah, that took us, took us a good 35 minutes, just 45 minutes to work through it. With me guiding, it'll take you a while to grind through one of these type of problems. Yeah, so it's hard not to make a mistake going through. Like, I think I made one, you caught it, right? So yeah, it was a calculator error, but yeah, just go through it. Slowly check your numbers and make sure you're using the right process. That's the part I care about. You would never do this completely on your own. Somebody would always look at it, go through it, and check it. So
I did get the scientific notation. I was doing the exponent on
is it the which button? Yeah, that's the one. That's the one. So on an HP, like if I want, what is it, something to the 4th here, 12 to the 4th, I just enter the 12 and then I enter the 4 and then I hit this button, which is Y to the X. So
taking so many advanced.
no, yeah, takes a while to grind through that. Questions?
I have a question.
Yeah.
So I having a hard time coming up with the right answer with the last thing we calculated.
The deflection.
Yeah, and so that's. I'm confused as to when we put it to the first, when we put it to the second, etc. Because I tried to do this and I just can't get that on.
So are you using a TI?
Yeah.
Yeah, so it's gonna be all bracket work. That's probably where the mistake is, but I would like the 5 times the 500. I'd probably bracket that because you want the 12 to the 4th to be separate from the 12 to the 3rd. So to separate those, I would just add additional or just break it into pieces, like get rid of those exponents, just rewrite it down as 5 times 500 times a number times a number. That's probably the safest way. Yep. And then this number down here, you can put in 1 7 and 5 zeros and not deal with any E to the E button or whatever, because that's what it is 175 or 170,000. That's what that is. Yeah. That'd be my recommendation. I mean, you could play with brackets until you get it and then you'll know, but there's always mistakes made with brackets and TIs on the darn final that just bug me. I mean, it's disappointing when you have the equation is perfect and then you get the wrong number here. That's a calculator error. Yeah, that's just a damn calculator error. The other thing is, however you do it twice. If you get the same number, then you're probably getting it. If you do it the second time and you get a different number, then it's like, oh shit. Yeah. Yep. That's a little how HP works, is you do each step. And then in the end, you do the function, like they're multiplied or they're added or whatever.
I have no faith in the calculator.
Okay, yeah, I love it. All right, that's it. I'm gonna send an email to all of you right now asking about how you'd like your final. And we'll go from that. Yep, absolutely. So what I'm gonna ask you though is, do you want it online or do you want it in person? Okay, then I'll be here Thursday. If anyone wants to come in and take it on Thursday, you can come in with us too. Yeah, no, I'm available if you have questions. That's the nice part of doing it in person.
Probably do it online at the same time.
Yep.